Okay, now in this slide, what we want to do is the following. The next couple of slides do the following. So here's this object that's rotating like so. There's the axis of rotation. And you saw that the further away you are from the axis, the faster you have to move because you're going in a bigger and bigger circle. And that's what this formula does. It relates the linear speed of this guy to the angular speed of the object. It relates the linear speed of a point to the angular speed of the object, or the angular speed of the object, the point as well. Okay. So if this object is rotating at an angular speed of omega, a point distance r from the axis of rotation is going at that speed. That's the linear speed. And if you're right on the axis, r is 0 and you're not moving. Okay. All right, so that's what this does. Now let's make sure that we understand the units correctly. Units of this would be meters per second. This would be meters. And so the units of this is 1/second. So angular speed is, again, radians per second, but radians is just a label. Okay, so this formula is relating the linear speed of that to the angular speed of this. Okay. And now what this formula is showing, what this slide is showing you, so there's this object that's rotating. Again, there's the axis of rotation. And if it has angular acceleration, that is, it's speeding up or slowing down. If it has angular acceleration, then a point r distance away from here, this point, if it's speeding up, it'll have a tangential acceleration. That is, its speed will be increasing, and there's the direction of the acceleration. Okay, now this point also has a radial acceleration. You guys remember that if you're going in a circle, even if you're going at constant velocity, that is, if you're not accelerating in that direction, because your velocity direction is changing, the direction of your velocity is changing, you'll have a radial acceleration. Okay. So every point on this object that is rotating will have a radial acceleration, even if this thing is rotating at constant angular velocity. Okay. But if it has an angular acceleration, then it'll have a tangential acceleration, and that's what this thing is showing you. So the tangential acceleration of this point is r times alpha. And the radial acceleration, or also the centripetal acceleration, is the speed, which is not shown here, v squared over r, okay, which is r times omega squared. I'll show you how to get, so the centripetal acceleration, so let me do this radial acceleration, or the centripetal acceleration, is v squared by r. Okay, and v is r times omega. V is the speed of the point distance r away from the axis of rotation. And so if you substitute that, r omega squared divided by r, this will work out to r omega squared. Okay, so that's what that is the formula shown here. Okay. All right. Okay, so the next two slides will look at an application. Now that you've learned about rotational motion, so this is the kind of stuff you'll encounter when trying to solve problems. Okay, so you guys have all seen CDs and DVDs and all that. So here's how the information is put on the DVD or CD. So the information is laid on that track, and you see the track starts at the center and spirals outwards. Okay, now here's the deal. You use a laser to read the information on this CD. So for instance, so on that line, information is packed as bumps and so on. Okay. So this is our information. And here's a laser that's shining from the top. And when it hits a plane surface, you can have a high intensity, nice beam reflected. When the laser hits a bump like this, okay, the beam is scattered and your detector doesn't get any reflected light. So that's how the machine tells the difference between this and that. Anyways, so here's a physics fact. If the laser wavelength is that, the smallest, that's the wavelength, the smallest spacing between information can be equal to roughly the order of wavelength. So the smaller the wavelength you use, the more information you can pack. Okay, so remember that. Okay, so now let's get back to our slide. Okay. So anyway, so information on this laser, on the CD is packed on that line. Okay, it's spiraling all around. Now, as the CD is rotating, the laser is shining like that, the CD goes by, and then the laser goes outwards. Okay. Now, the deal is the machine is designed to read at a constant rate. Okay. So what you have to do is you got to make sure that, so here's the laser that's shining, and you have to make sure that a set amount of line passes under the laser per second. Okay, so the velocity of this line should be constant. Now, as the laser is moving outward, as it's reading more and more, as R increases, to keep that constant, the rotational rate has to decrease. Okay, so let me make sure you understand this. So V has to be constant, and as R increases, omega has to decrease. So when you're playing your CD, you have to design a variable speed motor because your angular velocity, the motor speed has to decrease as the CD plays on. Okay, so that's a very interesting application that you would have to solve as an engineer. Okay, now again, so coming back to the fact that, so coming back to this, again, like I said, the information is packed on this thing. Now, if you want to pack more information, of course, you want to be able to place the lines closer, and you want to be on the line, you want to place those bumps closer. And what is the limiting factor? Remember, I said it's the wavelength of the laser that you use. Okay, so red laser has a larger wavelength. Okay, so the CDs used a red laser, and nowadays you guys are aware of blue laser, Blu-ray DVDs. They use blue laser whose wavelength is smaller, and so Blu-ray can pack more information than the old regular CDs. Okay, so what this number is telling you is what this number is telling you is the spacing between loops is 1 micrometer, roughly the size of a cell. This is for the old red laser. Okay, so let's get to the slide, get to the next slide. So this tells you, so this is for a CD, a DVD, and a Blu-ray. Okay, so CD used a red laser, which had a greater wavelength, and a DVD used another laser, which had a shorter wavelength, so more information could be packed. The groove spacing could be less, about half. And for the Blu-ray that uses a blue laser, the wavelength is about 1/5 that of the CD. Okay, so let's see the information. A CD could pack only 3/4 of a gigabyte. A DVD could pack 5 gigabytes. And a Blu-ray, which uses a blue laser, can pack 25 gigabytes. Okay. So let's see the relevant information. Okay, so for a CD, the track length is 5.4 kilometers. That is, what that means is the length of this track is 5.4 kilometers. And 5.4 kilometers is about 3.5 miles. So this length is 3.5 miles. Okay. Okay, so for a CD, that's 5.4 kilometers, and the information packed is 0.7 gigabytes. And okay, so 0.7 gigabytes divided by 5.4 kilometers is roughly about 0.1 gigabyte, a little more over that, gigabyte per kilometer. Okay, roughly. All right, so for a CD, you pack 0.1 gigabyte per kilometer. And for a Blu-ray, this is 25 divided by 29, 1 gigabyte per kilometer. Okay, let me write this down. 0.1 gigabyte per kilometer and 1 gigabyte per kilometer. Okay, so when you went from a CD to a Blu-ray, you could pack 10 times more of the information. Okay, so the information density was 10 times greater. Okay. All right, well, let's compare that to your DNA. Okay, so in your DNA, in every cell, your 23 chromosomes have your DNA has all the information. Okay, and your DNA contains 3 gigabytes of information. Okay, and if you stretch out the all your chromosomes and stuff like that, your all your DNA molecule, it would stretch out to 22 meters in your cell. Again, that's what it would stretch out to. Okay, so the information density here is 3 gigabyte by 2 meters, roughly 1 gigabyte per meter. This was 1 gigabyte per 1,000 meters. Okay. So information in your cells is packed 1,000 times better than on a Blu-ray. So anything nature does is that much better. All right, and that was just a side story, and I thought it was interesting, so spend some time on it. All right, let me pause the video here a second. Okay.